Today we're going to learn about one other way to determine if a series is convergent or divergent. Now, up to this point, we have looked at series that are of a specific type. They've had the nth term test series, we've had harmonic, we've had telescoping, we've had geometric, we've had p-series. Now we're going to talk about what do you do if it doesn't fit one of those molds? What if it's a series that's a combination of two different types? You know, the top is a p-series and the bottom is a geometric series. What do you do? Well, there are several different tests that you can run to see if it converges or diverges. And one of them that we're going to learn today is the integral test. Now, there are some parameters that you need to know about this integral test. This is going to go back to infinite integrals, improper integrals, and review that topic and use the integration to find whether or not this thing is going to converge or diverge. The worksheet is very good at explaining why it works the way it does, and that's what we're going to walk through today. I'm going to add a few extra things to write down, but there isn't a whole lot to write on the front. So, this doesn't work on everything, but it does work on these two examples, and when we get to the point where we discuss the rule itself, we'll talk about when it does work and when it doesn't. Okay, we're going to start out by looking at the integral from 1 to infinity of 1 over x dx. Okay, here's the graph of 1 over x. We want to know the area under this curve starting at 1 and going to infinity. Okay, we've learned how to do that mathematically, but we're going to tie the integral to the series. So what I want you to do is we're going to estimate this with a left Riemann sum. All right, so up here in the little margin, I want you to draw a t-chart sideways, x and y, and let's put like 5 squares in it here. I need to do one more. 1, 2, 3, 4, 5. It says we're going to make a left Riemann sum with a base of 1. Okay, so that means your x's are 1 unit apart. All right. When we do a Riemann sum, remember that we plug it into the function that's in the integral. So if I plug a 1 in for x, what do I get? I get 1. What about a 2? 1/2, 1/3, 1/4, 1/5. Agreed? Okay. Now, if we were going to do a left Riemann sum, we would look at the first two pair of ordered pairs. Which y value is on the left? The 1 is. So that would be the y value I would use for the height. And what is the delta x, the base? 1. So the first term would be 1 times 1, right? Now then you would move over. Which y value would I use for this one? 1/2. I would use the y value of a half, but then the delta x is still 1. So down here, if you see, it's 1 times 1, 1 times a half, then for the next pair it'd be 1 times a third, 1 times a fourth, and lo and behold, that creates a sequence that we learned, or a series that we learned last class, the harmonic series, which is the same thing as this. Notice that this notation and this notation are almost exactly the same. The function inside is the same. The only difference is, instead of a sigma, we have a integral. Okay? From our previous section on improper integrals, we know that this integral is infinity for an answer, and it diverges, and it's the same term we used before. But let's go ahead and prove that one real quickly. Do y'all remember how to do this? The integral from 1 to infinity of 1 over x dx. We're going to have to do this quite often today. So let's review how to do an improper integral. Okay? Who remembers what we do?
You replace infinity with b.
Right, we replace the infinity with b. So we write the limit as b approaches infinity, integral 1 to b of 1 over x dx. Do y'all remember doing this? About 2 weeks ago? Now you take the antiderivative like you know how. What is the antiderivative of 1 over x? It equals ln absolute value of x. Did you remember to put absolute value on your quiz?
Yes.
Did you remember to put plus c on your quiz?
Yes.
Uh-oh. Okay, but does this one need a plus c or not?
No.
This one does not. We put the 1 and the b on the back side. Can you see what I'm writing? No, you can't. There we go. Okay, so we're going to come back to the next line. We're going to write the limit again. Limit as b approaches infinity. Now b is positive infinity. So if I take the absolute value of positive infinity, that's going to be positive infinity. So ln of b, I don't need the absolute values anymore, minus ln of 1. The absolute value of 1 is 1, so I don't need the bars anymore. So if I plug infinity in for the b, the natural log of infinity, is that infinity? The natural log of 1,000,000. Do you think the natural log of 1,000,000,000 is bigger than the natural log of 1,000,000? Probably. They just get, natural log of 2 is bigger than natural log of 1. They're just getting bigger and bigger and bigger. So that equals infinity, and it does diverge. We know that the integral equals infinity, and it diverges. The Riemann sum that we did, which is the same numbers added together, is an overestimate because the rectangles are sticking out above the curve because the curve is decreasing. So if the Riemann sum diverges and it's actually too big, then the series is also going to diverge. Our Riemann sum over approximates the integral. So if the integral is divergent, then the series must be divergent as well. Now, we already knew that that series diverged. We did it last class. It's the harmonic. We said that the harmonic always diverges. But we just kind of proved it a different way using the integral test. But it's a good one to use because it's easy to see. So, what did we conclude? We concluded that if the integral diverges, the series will diverge as well. Okay? All right, now let's look at 1 over x squared. Different function. We're going to use a right Riemann sum with a base of 1 to approximate this integral. So I'm just going to do like 3 terms this time to get the point across. 1, 2, 3. Plugging in 1 for the x, that's still 1. Plugging in 2, that would be 1 over 4, right? Plugging in 3, that would be 1 over 9. So if we're going to do a right Riemann sum, we start with the 1/4, don't we? So it's 1 times 1/4, 1 times 1/9, 1 times 1/16, which is this pattern right here, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, which we could call 1 over n squared as long as we start at 2. Does that make sense? As long as we start at 2 and we do this. This is 1 over n squared, and once again, they match, okay? From our previous section on improper integrals, we found out that this improper integral actually comes out to be 1. And because it came out to a number answer, it does converge. Okay, I'm not going to do the math for that one just to save some time. Now, since this series of numbers under approximates the curve is going to be less than the curve, even if I added one more square with a height of 1 because it starts at 2, because this, did you notice that this value here is different from that value there? You can adjust it. Adding 1 to this will still be less than the curve, because if I added a square that's 1 unit tall and 1 unit high, it'd still be under the curve, and I'd still have curve left. So this is also convergent. So basically what we found is whatever the integral does is what the series does. The only thing is it has to hold these 3 conditions. The function that you're going to do this to must be positive, i.e. above the x-axis, it must be decreasing, and it must be continuous. Now, what you pasted into your flip chart, which we'll look at later, change the order of this to P and then D and then C, positive, decreasing, continuous, because that makes an acronym like PEMDAS. We're going to call it Please Don't Cuss. Please don't cuss. Okay, PDC, positive, decreasing, and continuous. Now, what this is basically saying, then the series and the integral either both converge or both diverge. Whatever the integral does, the series does. And that's how you can tell whether it's going to converge or diverge. It connects the idea of the infinite series to area under the curve. The series and the integral both do the same thing. That's what you got to remember. So put a big old star out to the side. This is the integral test information. Whatever the integral does, as long as it's positive, decreasing, and continuous, the integral and the series will do the same thing. Either both converge or both diverge. I'll show you how you have to write it down. Now, back on the flip chart, we had the CAN acronym. The C was the conditions. This is the one the conditions are real important. If it's not positive, decreasing, and continuous, you can't use this test. There's other tests that we're going to learn later that you can use. So for the worksheet, however, everyone is going to fit the mold, but you really ought to double check just to be sure. Okay, any questions to this point? Okay, let's turn to the back. Let's put this to practice. Let me show you how this works. Okay, number 1 says apply the integral test to these two series. So we have the series n equals 1 to infinity of 2n over n squared plus 1. Now this is not a p series, even though it's got an n squared because of the plus 1 on the bottom. And it's got something totally different on top. P series is 1 over a power squared. So this one is not a p series. We have to use something other than a p series or a geometric test or something on this. Now, the graph of this is right here. Kind of looks like a playground slide. Now, you must always check to see, first of all, is this graph positive? Is it always above the x-axis? Yes, because this is only a quadrant 1 graph. Is it decreasing past 1? It has to be decreasing past the number on the bottom of the series. 1 is right here. Yes, it's decreasing after that. And it is continuous. So what we write is we write f of x is positive. You can use shorthand. Positive, decreasing, and continuous. That has to be in play before you can even do the integral. So you must write that down every time. Okay, so now we change the series to an integral. What do you think my limits of integration are going to be?
1 to infinity.
They're going to be the same as they are on the series, 1 to infinity. And all we do is rewrite this with x's. So it's going to be 2x over x squared plus 1 dx. There we go. So we just changed the series to an integral, an improper integral. Okay, now we got to go get our minds back in integral mode. Okay, anytime you see an integral and you see a fraction, what's the first question you ask yourself?
If it's u substitution.
If it's u substitution and being more specific, is the top the derivative of the bottom?
Yeah.
In this case, is the top the derivative of the bottom?
Yes.
Exactly. Yes, it is. So I don't even have to do a u substitution since I don't need to put any extra things in there. I can immediately go to the answer, but I first have to change it and put the limit in. I almost forgot to do this again. Limit as b approaches infinity, integral 1 to b, 2x over x squared plus 1 dx. Now, because the top is the derivative of the bottom, what kind of antiderivative will this be? ln. ln, absolute value of x squared plus 1 from 1 to b. So when I come to the next line, I rewrite the limit to remind myself that's what I'm doing. So I plug in b first. That's ln of absolute b squared plus 1 minus ln absolute 1 squared plus 1. Now, in actuality, I don't need the absolute values on either one of those because they're both going to be positive anyway. But if you put them, it doesn't hurt anything. It's okay. So if I take the ln of infinity squared plus 1, is that going to infinity? Yes. So this limit is infinity. Therefore, the series diverges, because it was infinity, by the integral test. That's what you write. After you found whether the limit is either a number or is infinity, you write therefore the series does whatever by the integral test. The top line must be there, the bottom line must be there, or you will not get credit for the problem. We're just going to modify the problem slightly. We're going to take that n off the top. See the next one here? 2 over n squared plus 1. That's this thing right here. So is it positive? Yes, it's above the x-axis. Is it decreasing? Yes. Is it continuous? Well, it's a dotted line, but it's really continuous, okay? So f of x is positive, decreasing, and continuous. So we can now write it as an integral to evaluate it. So it's the integral, once again, from 1 to infinity of 2 over x squared plus 1 dx. Okay, so let's change it to limit form. The limit as b approaches infinity, integral 1 to b of 2 over x squared plus 1 dx. Okay, once again we ask ourselves, is the top the derivative of the bottom? No. Can I make it that way?
No.
No, because it's missing an x. If it's ever missing an x of any kind, it doesn't work. You can't fix it. So what we have to do, though, is think about what the alternatives are. You just took a formula quiz. Take the 2 off, make it a 1. 1 over 1 plus x squared. That's a special formula, antiderivative. Does anybody remember what it is? It is tangent inverse. Very good. So what's going to happen is the 2 is going to move outside, so it has a 1 on top. And then this is a classic tangent inverse. So this is now going to be 2 equals 2 tan inverse of x from 1 to b. So I'm going to go to the next line, rewrite the limit. This is a great time to rewrite it. It's right here. So we have 2 tan inverse of b minus 2 tan inverse of 1. Okay, now, tan inverse, you probably would think, oh, I just plug in infinity, it's going to be infinity. No, it's not. Tan inverse actually looks, it's a tangent on its side. And it looks kind of like a logistics curve. Do you remember this? Take one of those little tangent things and we kind of twist it and turn it on its side. So the limit as x approaches infinity is that upper asymptote. Do you know what that upper asymptote is? Okay, it's the same thing as if you turned it sideways. Some of you said the right answer and some of you haven't. So where are the asymptotes on regular tangent? Negative pi over 2 and pi over 2. Okay, so the limit as you approach infinity is pi halves. So it's 2 times pi over 2 minus 2 times the tangent inverse of 1. Okay, what has a tangent, what angle has a tangent of 1?
45.
45, because the sine and cosine are the same, right? What is that in radians?
Pi over 4.
Pi over 4. So now we just clean this up. So 2 times pi over 2 is pi. 2 times pi over 4 is pi over 2. And pi minus pi over 2 is pi over 2. Therefore, the series converges by the integral test. Okay. A point that I need to make is this. Do I know what all those numbers in that series are going to add up to be? The answer is no. The pi halves, the only thing it tells us is yes, it converges. It doesn't tell us what the number that it converges to is. It might be pi halves, it might be something totally different. Okay. We don't know the sum. Okay, and we can't find it. Not with what we've got right now. Okay? We don't know the sum. Let's move that over just a little bit. There. Okay? It doesn't necessarily converge to pi halves. The only ones you can find the sum on are geometric and telescoping, and that's it. And this is neither. All right? So let's practice a few more of these just to see if we've got the system down. Okay? Now what makes the next two a little bit harder is the fact that they don't give me the series, because then I don't know what to integrate. So I've got to figure out what the series is. So what we do is we draw our sigma. Go ahead and draw your sigma. Now some of you are going this is going to be easier than others. I know. It took me a while to figure this out too. What do you notice about the numerator of all of these fractions? It's always 1. So I can put a 1 on top. I know that for a fact. Do you notice that all of the denominators are powers of e, except for the first term? But is the first term a power of e really?
It is. Yes.
It is. What is it?
1.
E to the, no, not e raised to the 1. It's e to the 0, isn't it?
Oh, yeah.
You follow me? So what I can do is I can put e to the n and start my n's where? I have to start at 0 and go to infinity. Okay? So that's how I figured it out. I knew the top was 1. I knew that the bottom was a power of e. And so then I kind of played with it a little bit, and so I could figure out what my limits of integration are going to be.
Does it matter if you put the whole fraction to the power of n?
No, it does not. I could go ahead and put the whole fraction to the power of n if I wanted to, but for integrating purposes, it's going to be easier actually to leave it like this. Okay? So, are these always going to be positive?
Yes.
Yes. Are they getting smaller?
No.
E, think of E as 3. 1/3, 1/9, 1/27. Are they getting smaller? Yes. And it's continuous, therefore I can use the integral test. So f of x is positive, decreasing, and continuous. You have to write that every time. Now I can change it to an integral. What are my limits of integration?
0 to infinity.
It is 0 to infinity, exactly what's on the series. So this is 1 over e to the x dx. All right. Now, okay, how do we integrate this? Is the top the derivative of the bottom? No. How do we usually integrate e's?
Just do the copy and go.
It's a kind of a copy-paste thing, right? But I can't copy and paste where it is. So let's move it upstairs. So while we rewrite it as a limit, let's move it upstairs. So limit b approaches infinity, integral 0 to b of, how do I write it? E to the negative x dx. Are we good so far? Okay, now we got to just think. If it's a copy-paste, this would just be e to the negative x. However, is the derivative of my answer equal to the question? No. What's it missing?
A negative.
It's missing a negative, so I got to put a negative on it. Does that make sense? Because if I do a copy-paste with this to here, and then I have to multiply by the derivative of the exponent, then it would turn positive. Okay? So, bracket 0 to b. So, we come to the next line, limit b approaches infinity. So I have negative e to the negative b minus negative e to the 0. I don't need to write negative 0. Anytime you see a negative exponent, always change it to a positive before you start deciding whether it's going to infinity or not. Okay? So this would be negative. How do I write this with a positive exponent? 1 over e to the b. Do y'all agree with that? Plus, what is e to the 0? 1. So now if I plug infinity into this b, I get 1 over infinity, which in limit land approaches what? 0. So it's 0 plus 1. I'm running out of room. So this is 1. Do y'all agree with that? This is going to 0. So therefore, the series converges by the integral test because I got a number answer. Let's try number 3. So first thing we got to do is we got to write our sigma. Got to figure out what it is. Okay, I'm going to stop for just a minute and I want you to brainstorm that. If you want to talk to somebody about what you think the sigma is going to be, see if you can come up with what the sigma formula is going to be and what the bottom and top numbers are going to be. What do you think? I know this is the hard part. There's actually on some of these more than one way to write it, depending on where you start your bottom n. Raise your hand if you think you figured it out. I'm not going to necessarily call on you. Who thinks they figured it out? Not too many people. Okay. What's the top going to be? Can you tell me what the top is? 1. Now the bottom has 2 and then 3 and then 4. Now that some of you are bothered by that, it doesn't start with 1. That's okay. You can say that n starts with 2. Doesn't matter where you start. Go to infinity. So how would you write this with n's? N ln of n. N ln n n n n n. And we got some redundancy going on here, right? Okay. All right, are all those fractions going to be positive? Yeah? Are they getting smaller? Yes. And it's continuous, so we can write f of x is positive, decreasing, and continuous. So we can now write our integral. I'm going to draw a little line here. That's too much crowding. So it's the integral from 2 to infinity of 1 over x ln of x dx. Okay. Now, top's definitely not the derivative of the bottom. But is 1x the derivative of the other, possibly? Which one do you think u would be? Ln of x, because du would then be 1 over x. So I'm going to go ahead and do a u sub for this one. So u is ln of x, du is 1 over x dx. I've still got to change it to limit form, but I'm going to do the limit form and the b thing at the same time. Now, with these problems, I personally prefer to change it to u's, integrate it, and change it back. Okay, that way I don't have to mess with these limits of integration. All right, so here's what I'm going to do. The limit as b approaches infinity, integral 2 to b. Now, 1 over x and dx make your du. Do you agree with that? What is the rest of it? Just u? It's 1 over u, which will eventually be an ln. So this is the limit as b approaches infinity of ln of absolute value of u, which I need to change back to ln absolute value of ln of x from 2 to b. So this would now be ln of b minus ln of 2. The ln of b, the ln of infinity is going to infinity, and the ln of that is still going to infinity. So this answer is infinity. Doesn't matter what the ln of 2 is, it's still going to infinity. Okay, therefore, 3 dots in a triangle. What do I write? Series diverges by the integral test. Very good. Just get in that habit every time. Write it down. Okay. Now, do you think number 4 would be easier or harder? The way the problem starts. I already know what my summation is, don't I? I don't have to figure that part out. They gave it to me. So all I need to know, is it going to decrease? Now you may want to write out a few terms to see. It's up to you. So 0e to the 0, that's going to be 0, okay? And then 1 over e to the 1 squared, 2 over e to the 2 squared, and so on. Okay? Notice I put it on the bottom. All right, this one's a little tricky. Is this thing positive? Yes, 0 can go either way. 0, we don't need to worry about it. Okay? Are those fractions getting smaller?
Yes.
The numerators are getting bigger, but the denominators are getting bigger faster. Does that make sense? And when that happens, it is definitely decreasing. So, f of x is positive, decreasing, and continuous. So we write it as an integral. 0 to infinity, x e to the negative x squared dx. Okay. Okay. 2 x's, can't combine them? Probably u sub, or possibly integration by parts. I have not seen an integration by parts question in this section. They try to keep the integrals pretty simple. Okay? Is one of the x's potentially the derivative of the other? Yes. If I made the exponent u,
Oh, yeah.
I can modify the x in the front to be du, can't I?
Yeah.
Okay, so that's what I'm going to do. So once again, let's do a u sub. So u equals negative x squared. Du equals negative 2x dx. So this needs a negative 2 and a negative 1/2. Is this coming back to you? Yes. So this will now be the limit as b approaches infinity. I'm not going to mess, oh wait, I forgot my negative 1/2. Negative 1/2 integral 0 to infinity. This and this is du, right? What's the rest of it?
E to the
It is e to the u. Do y'all agree with that? Because u is the exponent. Oops, this is supposed to be a b right there. Dang it. All right. I'm going to do this all in one step because I know you guys can handle it. So negative 1/2. What's the antiderivative of e to the u? It's just e to the u, which I'm going to change back to x's. E to the negative x squared from 0 to b. All right, let's try plugging this stuff in. So this will be negative 1/2 e to the negative b squared. I forgot to write my limit. Let's do that real quick. Limit as b approaches infinity minus negative 1/2 e to the 0. Once again, I have a negative exponent. Don't try to evaluate until you make that negative exponent positive. So this would be negative 1 over 2 e to the b squared on the bottom. Are we good with that? Negative b squared goes to the bottom, becomes positive b squared. Plus 1/2 times 1. Okay? Now remember that b is becoming infinity. B squared is an super large infinity. So the bottom is getting closer to infinity, which means the whole fraction is getting closer to 0. So this is 1/2 for an answer because this is approaching 0. Therefore, what? Series converges by the integral test. Okay. Do you have any questions for me? So, just in a nutshell, let's go back to our flip chart. You all have your flip chart, right? Pull those out real quick. Let's look at see what it says on here. The integral test, best used when the integrating is easy. Now, as of right now, this is the only method we know to tackle problems that do not fit the G series, geometric series, the P series, any of those molds. Later on, you're going to have choices. But don't do the integral if the integral's ugly. This whole worksheet, you can do integrals. It's not too bad. Conditions that f of n is positive, decreasing, and continuous. Please don't cuss. PDC. You've got to write that down. You apply the fact that the series and the integral either both converge or they both diverge. Now, I believe this is more than you really need to write. She wrote, since the integral converges or diverges, the series also converges by the integral test. I believe it's sufficient to just write, therefore the series converges, based on the answer you get. But I will double check with her. Okay? Any questions?